Hello, everyone. Welcome to the podcast. I'm your host, Kishan, and today we have a very special guest, Dr. Kaicheng Jia. Dr. Kaicheng Jia is currently working as a research fellow at the Beijing Graphene Institute, China, where he leads a research group focusing on single crystalline wafer. He received his bachelor's degree from University of Science and Technology, China in 2016, and later joined Peking University for his PhD. Dr. Jia's research interests have centered on growth methods, batch preparation, and equipment research aimed at producing single crystalline graphene films. He has secured more than 17 patents and has published 19 peer reviewed journal articles. Dr. Jia, it's a pleasure to welcome you on the podcast. How are you doing today?
Fine, thank you, and thank you for the introduction.
You're welcome. I'm very curious to know a bit more about this very interesting type of a carbon feedstock that we use during CVD. And you have been working with a copper containing carbon feedstock for the growth of a super clean graphene film. Could you tell us a bit more about what is a copper containing carbon feedstock?
Sure. The common carbon feedstock we use is the gas feedstock, such as the methane, and the carbon-containing carbon feedstock is the solid power, containing the copper and containing the carbon species for the growth of graphene.
Very interesting. In during the CVD, why do we need a feedstock that would have copper?
Uh, because we need in the CVD chamber, there are gas phase reactions and surface reactions. When for the graphene growth, the side reactions in the gas phase would form the most contamination. So to solve this combination, we need to add supplement copper to compose the carbon species into small species, and finally we can get the super clean graphene. So that's why we use this novel copper-containing carbon feedstock.
So, in a way, in order to address the amorphous contamination during CVD process, you have, let's say, tested a copper containing carbon feedstock. Is that correct?
Yes,
So, could you tell us a little bit more about what is the amorphous contamination during a CVD process?
sure. In the 3D production of graphene is in the high temperature chemical reactions. So there are many side reactions in the gas phase. When you put the uh, carbon feedstock in the chamber, they will first decompose into the active carbon species, and then this carbon species will form the larger carbon clusters. When these large carbon clusters adopt onto the surface of the graphene, the copper underneath could not decompose these clusters into small species, and these clusters would form the amorphous carbon, and finally the carbonation on the surface of graphene. So that's the formation mechanism for the contaminated CVD graphene.
Now, such an amorphous contamination that is, let's say, occurring during the CVD process depends also on the growth conditions, right? Such as the precursor conditions. Is that correct?
Yes.
Are these contamination particulate matters or can they also be thicker films?
Uh, there are films. Uh, we have got the uh, we have figured out the structure of this amorphous carbon by TM characterization, and we can see that the amorphous carbon is not, as it suggests, totally amorphous. They are
Hmm.
mainly the sp2 carbon, but has the 5 or 7 rings. So they are the continuous films on the graphene films.
Very interesting. And in How did you manage to remove such an amorphous contamination during the CVD process?
Okay, there are two main strategies. The first, as I mentioned above, is to add some copper-containing carbon feedstock with the aim to increase the copper vapor amount in the CVD chamber. So the gas phase reactions would be improved by this supplied copper vapor. Then no more amorphous carbon will be formed in the gas phase, and uh, they will not show on the surface of graphene. The second is that the amorphous carbon contamination and the graphene has different reaction activity. So you can use, for example, the carbon dioxide to age this amorphous carbon contamination, but not destroy the lattice of graphene. There are two strategies. We call this the growth of the supergreen graphene in the 3D chamber and the post-treatment to remove this amorphous carbon.
Can you tell us a bit on the type of copper containing carbon feedstock that you use?
Actually, we have searched a lot of the carbon-containing uh, five, copper-containing carbon feedstock, and we finally choose the copper acid as the best. So you should consider that this carbon feedstock uh, should be used to as a feedstock for the graphene growth. So the carbon species should be carefully selected. And you should also care about the security of the CVD chamber.
So you mean to say there could be a risk of, let's say, potential damage during the CVD?
Yes. So you should, for one thing, you should carefully select the type of the chlorocarbon carbon feedstock. The second, you should design your equipment to make a better control for the introduction of this chlorocarbon carbon feedstock.
Okay. So are there any other safer methods, or let's say non-gaseous precursors that we can use to achieve a super clean graphene surface? Because there was also an article where a copper foam, for example, was also placed on top of the copper foil to achieve a cleaner graphene surface during CVD. Could you please comment a little bit on that?
Of course, uh, as you mentioned, you can try anyway with the aim to increase the amount of the copper vapor in the CVD chamber. The copper foam is a better choice because it is porous and with large specific surface area, so it can provide the most of the copper vapor into the CVD chamber.
And how does the precursors and the growth conditions influence?
So you can see that the gas-phase reaction will be promoted by the additional copper catalyst, and you can see that the growth rate of graphene will be accordingly improved. So you can grow the modular graphene film with less time.
So are we talking on copper?
Yes,
I see. So these are some form of a soft graphitic films that form.
of course.
I see. I see. And what are some of the major challenges related to this approach?
The most challenging thing is that you should carefully control the amount of this copper into the CD chamber. For instance, if the copper you introduce in the chamber is to a very large amount, then the graphene growth the rate of the graphene growth will be increased too much, and the dormant size of graphene will be accordingly small.
In one of your works, you also utilized titanium tetrachloride to assess the presence of amorphous contamination on CVD graphene after the CVD synthesis, right? So, could you give us a brief background into the choice of titanium tetrachloride? How did you come to this?
Yes, that's a interesting question. You know that the clean graphene surface and amorphous carbon contamination is different in the surface property. When we choose this option, they will prefer to adopt on the contaminated graphene surface, not the clean graphene surface, because clean graphene surface has no damping bonds.
In terms of the copper atoms from the copper containing carbon feedstock redeposition on the growth substrate, is this a risk during the CVD synthesis?
Actually, that's why we choose the copper-containing carbon feedstock, because the copper atoms we introduce in the chamber will finally integrate into the bulk copper substrates. They will have no influence to the whole CVD reactions.
So, are you also, let's say, certain that you would not have copper deposition on top of the synthesized CVD graphene?
Yes.
Very interesting. And so, in this case, how do you transfer the graphene films that is grown on such substrates?
The transfer of graphene mainly depends on the purpose of uh, your transfer. For instance, for the common characterization of the graphene film, we'll use the commonly reported white polymer resistance transfer method. For the device fabrication, we will try the dry transfer method to decrease the doping effect. And to evaluate the cleanness of graphene, we will use the TM grid, and we will use this polymer-free clean transfer method to fabricate the super clean suspended graphene film.
And are there any risk involved of the precursor containing the copper deposition on the CVD chamber?
The copper deposition is inevitable in the CD chamber. So you can change the cost tube regularly.
So that means so the copper containing carbon feedstock does deposit on the walls of the CVD chamber. So after a couple of CVD sessions, we'd have to replace the quartz tubes.
Mm. Yes, the copper deposition rate will be increased compared to the CVD growth without the copper containing carbon feedstock.
Okay, that's a good information to know. Um, on the topic of single crystalline CVD graphene films, could you tell us a bit on what is single crystalline CVD graphene films?
Mm. Okay, the single crystal graphene film is that we can control the every graphene domains you grow. It has only one orientation. Then you can get the single crystal graphene film with extended growth time that has no grain boundaries.
So these are graphene films with no or minimal grain boundaries.
Actually, we hope it has no grain boundaries, but actually it may minimum grain boundaries.
Right. So it's clear that from a substrate point of view, it is possible to have a single crystalline growth substrate, which is having a uniform crystallinity all across. But however, the growth kinetics do play a role to determine the grain boundaries in this case.
Um, Actually, the growth of graphene with single crystalline or polycrystalline has no difference in the basic growth, but the effect of substrates is different. For to grow the single crystal graphene, you should first have the single crystal growth substrates to make the aligned growth of graphene.
And how does the growth kinetics differ when we compare the polycrystalline CD-Graphene and the single crystalline CD-Graphene growth kinetics?
Actually, the growth schedule of graphene is the same for the single crystalline and the polycrystalline graphene. The basic is the nucleation of the graphene domains and the enlarge of the graphene domains and the graphene domains into the continuous graphene film. They are the same, but the difference is the nucleation. The graphene domains is aligned or misaligned determines the final graphene film is a single crystal or polycrystal.
And from a growth substrate point of view, so you had the opportunity to, let's say, explore both wafers, single crystalline copper wafers, as well as foils. Is there any particular advantage of one over the other?
Yes, for the fabrication of the single crystal graphene wafers, we have first used the single cipher as the epitaxial substrate. Then we deposit the copper film on the sapphire surface, and with the high temperature annealing, it will become the single crystal copper 111 wafer. And for the single crystal copper films or copper foils, it's different because we will put the foils in the high temperature retention chamber, and with the high temperature annealing, you can get the single crystal copper foils with many other crystals, not only 111, but such as 10, 100, 110, and many single crystals.
And so, let's say, rewinding back, maybe 10 years ago, many of us used to use these polycrystalline copper wafers that were commercially available, and there was a lot of surface corrugations. And so, in when we compare those with the single crystalline copper foils, are we now able to have an ultra flat surface roughness also on copper foils?
Of course, the single crystalline copper foils is is flatter than the polycrystal copper foils, and the single crystal graphene wafers is the ultra flat, with the surface roughness less than 0.5 nanometers.
Right. So in case of the copper foils, I suppose this was achieved using electropolishing, and does the high temperature annealing also help flatten the copper surface?
Uh, Actually, in our experiment, when we use the copper foils, we will first use the electrical polishing, as you mentioned, to uh, increase the surface flatness and decrease the contamination. And then we will put it in the chamber to undergo the high temperature annealing to finally obtain the single crystal copper foils.
Okay.
But you can only choose the copper foils with high purity, but is more expensive.
Okay. You've also had the experiences working on CVD systems, right? So, do you have a particular preference for hot, cold, or a PE CVD system?
Yes, the difference between this hot wall, cold wall, and the PCVD CVD system is their heating mode. You see, the hot wall CVD chamber is commonly observed. The cold tube will be the reaction chamber, and the resistance wire outside will be heated from the outer wall to the final interval of your sample. Then you can achieve a uniform temperature distribution. Well, the cold CVD system, the thermal energy is concentrated on the substrate. Only substrate is heated, so the outward of the chamber is cold. As its name suggests, the cold CVD chamber. The PCD chamber is different from the above two system. It used plasma enhanced camp wafer deposition. So hardly grown the 2D graphene film by PCD. You can often grow the graphene nanowalls because of the effects of this electric field.
So, do you have a preference for either hot wall or a cold wall system?
It depends on the graphene films you want to grow. For the grow of the single-crystal graphene wafers, we will use the hot wall CVD system to achieve the uniform temperature field and gas flow field and better control on the growth conditions of the graphene film. Then you can finally grow the graphene with high quality and high uniformity. For the growth of the large area, a polycrystal graphene film will use the cold-wall CVD system because the cold-wall systems can increase the size of the graphene sample to the meter scale. And when we combine the cold CVD system with the low-to-low technology, we can grow the hundreds of meters long of the graphene films with high growth speed and low cost. It depends on the purpose of the graphene
Right.
films.
Okay. And in terms of growth rate,
Yes,
so how does the growth rate of the CD graphene films compare in a hot wall system and a cold wall system?
uh, actually, the growth rate of graphene uh, is faster in hot wall than cold wall because in cold wall CVD system, the temperature in the gas phase is low, so the carbon feedstock is not preheated, and the gas fraction is suppressed. So this will all influence the growth rate of graphene film. But the advantages of the cold wall CVD system is that it has the decreased heating time and the cooling time. Then you can reduce the whole time you for the production of graphene films.
In terms of the current status and the trends of the CVD system, could you provide a brief insight into the progress so far during the last 10 years?
Mm. Actually, we can see that during the last 10 years, the CVD equipment for the graphene growth is become more larger, more automated, and more intelligent. And I think that the future for the growth of graphene, uh, just as I mentioned, the single crystal graphene wafers will based on the hot wall CD chamber with batch-to-batch production manner, and the low-to-low graphene films with low cost and high scalability will depend on the cold wall CD graphene system because the easy fabrication of the graphite heater. You know that the hot wall CD reaction chamber is the size of graphene is limited by diameter of the cost tube. You know the cost tube is commonly the size of cost tube is less than maybe 50 centimeters.
So moving forward, what are you currently excited about?
I'm currently excited about the controlled growth of single crystal graphene wafers, and I also excited about the final killer applications of these high quality graphene films.
And are there any pending challenges that you foresee in the CD-Graphene technology?
Uh, of course, there are two, I think, the main challenges. The first is to uh, grow the final, uh, the most high quality graphene films without the surface contamination, without wrinkles and folds, and with better layer number control. This is very difficult. Many reference or many have only sold one or two of them, but they can't sell all of them to obtain the final graphene products. The second is about the yield, uh, the production yield, and the cost of the for the fabrication of this graphene film. You know that we have built the poly-scale production of single-crystal graphene wafers, rotary films, and so on. But we still devoted ourselves to increase the product yield of these graphene materials and to make these materials satisfy the downstream applications.
And on the topic of wrinkles that you briefly mentioned in the graphene films, are these wrinkles appearing on the growth substrate, or is it appearing during the transfer stage?
Actually, the wrinkles of graphene was formed during the cooling of the graphene after the graphene grows because the thermal mismatch between graphene and underneath metal substrates. And during the transfer of graphene film, uh, you will uh, create more wrinkles on the graphene film because of this transfer. Actually, for the device application, the wrinkle is a very uh, specific challenges. You know that the wafer scale device, when there are wrinkles, the related device will not work.
Right.
So we have devoted to the finally wrinkle-free single crystal graphene wafers.
Okay, on that note, Dr. Jia, thank you much for joining the podcast.
Thank you.